Thank you, Michael. Our fourth guest this evening is the only member of the panel for whom I wish a 10-second delay had been invented, because I've worked with him on various events where that would have been useful. I think he's the only MIT alum on the panel. He's an engineer by training. I speak with Jamie Hayward, who's the co-founder of two thoroughly unique organizations. I won't say any more about them because I suspect he will. So, Jamie, please welcome.
So first off, I started growing a beard to make myself look more credible, like George. I'm fairly certain it's an epigenetic effect, but we're going to study that later. And second off, to further George's questions of Kevin's, I made the deal that if we were going to do one slide, he had to really enforce it. And I want to make an observation. That the most established and important person brought none. And those two of us sort of visionary founders that are still involved in our organizations came with our components. I'll tell you about this one in a second. And Michael, as the professional CEO brought in with the company You Should All Invest, managed to take the one slide personalized introduction and convert it. By the way, animations don't make it one slide. It makes it seven. So. Just as a quick thought, I want to share that. If you want to take one thing home tonight, if anyone you know or love has cancer, you should have them do a Foundation Medicine sequence right now, without question, without pause, without hesitation. The money is, without question, worth doing. And in 6 months, I may have an entirely different recommendation to company for you. So I think that gives you a sense of just how fast this field is moving and how important it is, because a year ago, there wasn't an option. In fact, I was talking to a good friend of mine who was dealing with his wife, and he came to me and asked me a question. I went through it, and I said, you could get the sequence done, we could do it at NOMI, we can do it at some place, but making meaning out of it is going to require you engaging yourself full-time for the next 6 months in the skills to do so, to do anything from it. And so I think the step has occurred, not just that the sequence exists, but that you can do something meaningful with it. And it's guys that bring 7 slides to a 1-slide deck that are going to make that possible. So what's this slide about? So this is a wood cutting of the Gutenberg press, and I chose it because I think that we are standing at a moment where it's not just that the printing press has been invented, but that we're going to have to figure out what it does to society. And the two institutions that I have been involved in, ALS TDI, where we had a really big lab, the biggest lab in the ALS. I did the first stem cell transplant in the field, went from concept to my brother in 18 months, including primates and short-term and long-term rodent talks. You can do anything in medicine if you want to do it. You can do it legally, do it properly. It's possible to get anything. I think what's complicated is this is not a very democratic system. This is a system that does not allow for the information to flow to the individuals involved that can make a difference in their own lives. And we all have these secret networks where those of us call friends of ours that want to know how to solve things. I get a call once a week from someone who's sick, and we connect them to our network of people inside the system with the most advanced tools. And that's the way it works now, and maybe Foundation will transform that in the traditional way. But I actually think it's going to take a lot more than that. And I think that we have to think about who has access to this press, to the Bible, to this information coming off of that. Patients like me, as an enterprise, is designed to solve a problem that I think is coming. And it's always good when you start a company to be years ahead of the market. And what we do is we ask people to collect all of their information about what happened to them, their phenome, human phenome, what their experience was with their diseases, what their outcomes were. And if you move away from diseases where we have precision, like cancer, where living or dying is the primary end measure of whether or not you're cancer-free, which are fairly establishable, to things that are much more subtle or nuanced. Are you depressed? How do you manage aging well? what is it like to live with inflammation in your bowels over time? What are these diseases that debilitate us, take us out of the workforce, but are more invisible? We know almost nothing about them in the medical system. The medical records, the storage of this information doesn't really give anything useful for us to apply these tools to. And I think the one thing I really want to point out, and I think this is going to be the gist of some of the argument today, or dialogue, or positive frameworks, depending on how you want to put it. The genome is the start, but it's interesting now because it's precise, because you can measure specifically things with 10 to the minus 7th accuracy. And to talk about that when you're talking about pharmacology, I mean, if we get 10 to the 7th accuracy in pharmacology, we get lucky sometimes. And the problems that we're dealing with in medicine require us to move from these precise elements to areas where we don't really understand, and this network becomes much fuzzier, much quicker. And I think the real meaning, and yes, genomics will affect your life, and yes, you should spend $4,000. You should wait 6 months and spend $1,000. It doesn't matter. And if you named your book the $10, you're going to get it at your sale, right? But I think what really matters is not the DNA, but the state of the machine. The state of the machine for how you are. How long is your beard? How gray is your beard? Why is it that way? And then the state of the molecular elements that go to that, your RNA and your proteins and your metabolites, all the technologies that are following on behind the genome. They're going to tell us the true meaning of health. Because everything else is measuring a disease. If you want to understand health, you understand what it means to be sick at a phenomic and a molecular level so you can correct it in a holistic and effective way. And meditation might be a better treatment than some of the things we're using. So let's start the dialogue.
Cool. So we're going to talk now for about half an hour and then open this up for questions. So we've got a lot of topics, we've heard a lot of points of view. Since we're here to talk about personal genomes, I'm going to start with your personal genome. I wanted to know if you've all been sequenced or genotyped. And if you have been, what did you learn from that information? You can start with Michael.
So I brought up 23andMe, and as I said to Anne, the CEO of 23andMe, when I met her, I think I was probably their first 50, within their first 50 or first 100 clients. So I sent it in, and at the time I paid $1,000 instead of the $99 today for the original version, and now I have to decide if I want the whole exome or not. And so I did that probably, I'm going to guess and say 4 or 5 years ago. And I felt like I had to do it. I've been in this space for a long time, and it was interesting to me. I know that it's kind of, in those days, it was wrought with errors. There's no doubt about it. And I started to learn that in the early days that my eyes are brown. Okay, well, both my parents are Italian, and there's a good chance that my eyes are going to be brown. And I learned about my earwax and things like that. And so, there's some fun stuff that you can do with it. And so again, it sounds like I'm taking a shot at 23andMe, and I'm not. It's just that we're learning more and more. And over time, this becomes more valuable. Fortunately, all of the risk ratios that have come out, at least as part of my personal profile, have been either 0.9 or 1.0 or 1.1, so I guess I'm a fairly average person. And nothing has really jumped out. Now, I'd say I'm fortunate because perhaps if there was a 5x, a 5.0 risk ratio for a certain disease, I would say I would have jumped on it a lot more quickly. And so there is value there. And yes, certainly the second something like this was commercially available, I did jump on it. But it's more, to this point in time, it's been more like just kind of a cool thing. It's been good to know. And I check in probably every 3 or 4 months to see what type of information has been updated. And, but I'm sure that's going to change. And as we get deeper into the genome, and it's not just looking at thousands and tens of thousands and perhaps millions of SNPs, but it's truly a whole genome. And we do a lot more research and understand what this stuff means. That genome is going to get a lot more value.
So I did have my genome also profiled by 23andMe about 2.5 years ago.
You didn't spend $1,000, did you?
400.
There you go.
Monday sale. Sitting next to the co-founder. Yeah, got a deal. I must say I've been a bad consumer of genomic information in that I have not spent very much time interpreting my genome. So I can't even tell you what it has, what it's told me. I'm pretty sure it probably does say that I'm black, I'm of African origins and such things, but yeah, I haven't really done much with it.
You might want to check that, Carl.
Yeah. and I should check my status for sickle cell anemia because my parents each have the trait. My sister actually does have the disease. So I was told when I was 5 years old I didn't have anything, but I should confirm that.
Check.
I learned I'm related to my brother, which I think made my mom happy. So either, you know, there's two different guys at the same time. I know, anyway, but
Parents are in the audience.
I learned. I mean, you know, essentially from a health standpoint, I learned very little. And in fact, actually, I think some of it's very misleading. You know, if you look at things like, I mean, I have a 4x risk of rheumatoid arthritis, so you know, I really don't know what I'm going to do with that one. But you know, things like you look at heart disease risk. I think that we have a dramatic overinterpretation of these extremely selective and overdriven sort of association studies. And so things like your cholesterol level and your parents' experience and your family's experience are far bigger drivers, and I think we tend to believe the genome over, you know, the data that we really know should mean something. So I think it's dangerous in that way a little bit. I found a couple fourth cousins that we've corresponded with, which was kind of fun. By the way, just to trump you guys, so you know, we thought it was cool, so we just bought it for everyone in the company. So I think Patients Like Me is the only company that has made 23andMe a standard company benefit. We bought it for every employee when it was $1,000. But you know, I'm doing my kids and stuff. It's fun. I do think you know, there is an important dialogue about this, which is, you know, genomics can be extreme. Well, actually, one of the cool things, Sergey Brin is immune to the norovirus, and I'm not. That was another useful thing I know. So, like, if I'm sick, he can hang out with me because we share DNA. Oh, the last one is, I'm sorry. If you're with someone at a bar and you say, "Would you like to swap DNA?" You have to be careful about how you say that because you know you can share DNA at 23andMe, and she misinterpreted it. It wasn't what I meant. One last thought about this that I do think is interesting. You know, Kari Stephenson and I were talking about, he's invented this really neat method for imputing someone's whole genome.
Kari Stephenson, the CEO of Decode.
Kari Stephenson is the CEO of Decode. He's one of the sort of amazing pioneers in the field. And he made this great deal. We went to the country of Iceland where he lives, and he said, I want to license Iceland. And Iceland said, okay, you can license Iceland. So they gave him every medical record of everyone that had ever lived in Iceland. And he started doing genomics on that. It was a remarkable thing. This is a wonderful record system, unlike the United States. And you can go back and look at all this stuff. So one of the things that I asked him is I said, you know, there's this data on unexpected paternity. And I'm curious what your data shows, because the high data, there's a couple studies that show us as high as 10%. And then the sort of commonly accepted numbers are 3 to 4%. And Kari said, no, actually, I'm getting less than 1%. And I've been asking myself the question, what is a number that represents the world that you want to live in? Is it a world where people do fool around a lot, or one that they don't? And that's the question, because the cool thing about Kari's method of imputing the entire genome from SNPs is that within a few years, we will know everyone that has ever had sex with anyone in the history of the world.
Follow that, George. We know you've been
I don't think we need a 10-second delay for me. So I may be the only person, apparently I'm the only person on the panel who's actually had their genome sequenced.
I'm trying to, but you're like going
no,
slow.
Sorry, I slowed it down specifically so I could trump Jamie. He is a member of the PGP and his genome is being sequenced, but we didn't want to have it happen tonight. So what have I learned? I was sequenced necessarily because I wanted to be. I did, but because our Institutional Review Board, IRB, requested that I actually feel the pain of the PGP firsthand. And I have. I was the first one to get a skin biopsy, and it was done in a way that we no longer do it. Anyone's curious, I can tell you, it takes a little while. But the way we do it now is quite nice. And with those skin biopsies, we established pluripotent stem cells, from which we can make basically any tissue in your body. In principle, we'll be making transplants this way. And so my genome was actually not, I'm embarrassed to say, not only sequenced once at 40-fold coverage, but several times. I've actually lost track of how many times we've sequenced my genome at high coverage and accuracy. And part of the reason is we've done multiple different cell types and gotten different answers. And so I thought this was interesting. In particular, the IPS line for PGP1, it has a mutation in a putative gene that's involved in cancer, NEK11. Probably not on your top of your list, Michael, but still, it's in the database. And that means I probably don't want to use that IPS line to make fresh kidney for me. I might want to try again, and we will. We'll keep trying it. And the irony is, these cell lines that we provide for the PGP for the world to use to test hypotheses that come out of genomes can be used again and again. And the fact that they're becoming a standard in synthetic biology, where if you want to test this hypothesis. And whenever we change the genome, we sequence it to make sure that what we changed is the only thing we changed. And this is a brave new world that we can do that kind of thing. The other thing I learned about my genome, going back to my genome rather than my clone's genome, is that I don't have hypertrophic cardiomyopathy. And that actually is interesting because a lot of athletes and regular folks die of it. And they have no clue. They drop dead in front of cameras, and that's the first time anybody knew about it. And any of you could, I'm sorry to say, okay? And so I think we don't, I think another business model for the genome is not like a cell phone. I'm going to whip it out every few minutes and say, hey, there's my genome, there's my genome. It's more like fire insurance or dismemberment insurance. There's something that you don't actually want to whip out every so often to use. Do you feel lucky is the point. If you feel lucky, don't get any insurance. Don't get your genome sequenced.
Let's just stay with the Personal Genome Project for a second, because you kind of launched this with an article in Scientific American in 2006, and apart from providing a means for people to get sequenced and collect other information, this is all made public. You have a website where this is all made public, and I know we have legislation that protects against gender discrimination, but I think this is still an area of great concern for many people, that genomic information somehow, somewhere along the line, is going to come back and hurt you. It's going to be used against you in some way. And you've been sort of lobbying, campaigning, and I wonder if you could just take a minute to explain why you believe that is perhaps a fallacy, I don't know if that's the right word, but why this open approach to revealing everyone's genomic information?
Well, first of all, this is not for everyone. We do everything we can to talk people out of joining our project, including making them take a test and other onerous tasks. We still have a lot of volunteers like Jamie, and we're very indebted to them. What's the question? Open information. Well, I think that the Genetic Information Non-Discrimination Act of 2008 does make it illegal for healthcare providers, health insurance, and employers to do it. But individuals dating one another can still discriminate. And I think that might have been Jamie's problem. A misunderstanding. Maybe perhaps there was too much understanding. Also, kids can discriminate against your kids on the playground, if you have the wrong genes, right? And so there's plenty of discrimination out there, and we don't want to sugarcoat it. Nevertheless, I think it doesn't take that much bravery. I mean, it's not like going to Iraq or to the moon in terms of bravery to be. I mean, sometimes some of my colleagues call the Personal Genome Project genetic astronauts. I wish we were that brave, but you know, I think it's more like your face, right? There's a contract we have with each other. We're going to show each other our face. But you know, if I have a disease that, you know, smallpox or something, you can tell from my face. You can tell whether I'm angry or depressed. You can tell my ancestry, all sorts of personal stuff. And the question is, should I be sharing that stuff with you? And the answer is yes. With the genome, we don't know. And that's why we need a cohort that will be our astronauts for us. And we can watch them. We can all watch and see whether they have a good ride or they blow up.
Michael, let me come back. Can I hit this?
So I actually think the PGP is one of the most important projects going on in the world today, because we really are asking the question right now about whether people who have not necessarily the public's good at heart will control who gets to live and die with information, or whether that will be something that is a public resource. And I think George has put out a very significant lobby, very significant position that says, let's just see if maybe we can build a society that is just and open. And I think that is a very, I mean, I don't think we should miss this. I mean, I think this is a moment like, you know, the people that are protesting, volunteers sharing this information are, to my mind, no different than the priests that protested the translation of the Bible to English because the people did not deserve or were not qualified to receive the Word of God. And I think this is the same. And I don't think we should sugarcoat it or say it any differently than that. I also think that we should also realize that this is over. I mean, $10, $1. I mean, the genome is going to be $1. This stuff. You're watching this technology move so quickly. I mean, I know
1.00.
I mean, you know, Michael. I mean, how you make investments when your price curve is going down like this is terrifying, right? You're buying machines, you're buying services. This is scary stuff. Like, you're trying to make decisions. And God, you know, I worship Jonathan and I worship all of these guys that are developing these machines. And I'm thinking, God, I don't want to be in your business because it's just like, you know, someone's going to invent something new next week and you're all going to be gone. So, I mean, Moore's Law, you know, is like a speed bump to this race. So if it's free, and if I could shake your hand and sequence your genome in my pocket, and we're talking 10 years is like realistic for that, there is no genetic secrecy. It's done. So I think the question that we really have to ask, which makes this even more important than just about who gets to read the Bible, is how do we begin to form a society where secrecy is not the method for preventing discrimination, but that we build a just society where we can allow humans to interact knowing that we are not all identical, we all have strengths and weaknesses and all kinds of consequences, and we build a society that works that way. And if I were in the life insurance business, I would be worried.
You know, one thing to understand, though, about as we talk about cost of the genome. So the cost of the sequencing and the reagents included in the sequencing today for what we do represents approximately 18 to 20% of the total cost of running a specimen through our laboratory, of the variable cost. So it's not necessarily if that price of the cancer genome, which is fundamentally different from the discussion that we're having up here about a $1,000 genome. It is, you know, it's beyond night and day what we're talking about. George mentioned, you know, getting a genome done at 40x coverage or 50x coverage. You know, you have to ramp that up to 500x or 1000x if you're talking about cancer tissue, and so it's much more complicated in this arena. But again, the cost of the sequencing is a small percentage of the overall effort as we think about employing this technology especially in healthcare going forward. And also just back to the notion of the information being available. So this is a great country. It really is. For all of our flaws, it's a great country. And so fortunately that means that we have the right to decide whether or not we put our genome out there. I think we'd be having a completely different conversation if there was a threat that we were going to be forced to have all newborns run a complete genome, to have their genome sequence for all newborns going forward. That conversation right now would be dramatically different than a voluntary effort because there is risk. That's the bottom line. I agree with these guys 100%. The risk is trivial in the grand scheme of things, but there is risk, and there's a difference between being forced to do something versus volunteering to do something.
Let's talk about how this information is going to be used in medicine. You've shown, and Colin presented this amazing, first-hand personal example. Patients are already being sequenced, cancer specimens are being sequenced in your lab. You've got fantastic technology. You've got an interface, or you're working on an interface that will be presented to the oncologist or the physician. You're finding mutations, many of which have never been seen before. It all looks very good, but there must be some challenges in really integrating this into today's healthcare system, whether it's regulatory problems or reimbursement or just getting physicians to understand this information. Can you talk about some of the challenges in terms of leveraging your genomic expertise into getting this into mainstream medicine?
Yeah, and I can comment on that from a couple of different perspectives. First of all, if you think about just the standard molecular testing that's routinely done in the world today, PCR-based testing, FISH-based testing, where we're looking at, in general, we're looking at single genomic rearrangements, single genetic changes or genomic changes in cancer. I'll focus on cancer. We still don't do that well. There's still challenges with IHC assays, the interpretation of those assays, the interpretation of an EML4 out FISH assay. It's still really difficult to, for the average pathologist to really look at these specimens and do the interpretation correctly. I say all the time, the average failure rate, take all comers, but the average failure rate in really good molecular labs in the United States for specimens that come through is approximately 20%. So what does that mean? That means every time, in this case, again, a patient with cancer, the biopsy is sent into a lab, they want to run a couple critical tests, 20% of the time they don't get the answers that they want because there's not enough tissue, something didn't work well, so they're just not producing the data. Next-gen sequencing, whole genome sequencing is not a little more difficult, it's logarithmically more difficult to do on a routine basis. And so to think about this going from beyond a couple of key centers in the United States and just permeating out there, it's going to happen, but I don't believe it's going to happen in the next 10 years. It's certainly not going to happen in the next 5 years. I think 5 to 10 years is probably, I could debate that, and I think that's a fair point. That would be a fair point of contention. So that's challenge number one, just the basic technical challenges of doing this everyday routine specimens. Remember, the difference between research, the difference between doing this on a blood sample, which is what we're talking about here, and doing it on a piece of cancer tissue is that if you're doing research, you can cherry pick you can get a nice big block of tissue with lots of tumor cells. It's actually not all that difficult to do. But if you're a laboratory and that oncologist or that surgeon had one chance to get the biopsy, and it's in a challenging location, and a biopsy is about this big, and that's what you receive, you better not fail 20% of the time. You better not fail 20% of the time. You better get it right. And that's really what makes this so difficult, specifically in the area of cancer. And then once we get through the technical challenge, we like the fact, that's why this is in a venture-backed company, and this is why my last company, which was acquired by GE Healthcare, is not doing this today. It's why LabCorp and Quest are not doing this today. It's really complicated. It's not ready for use in your average, even your average state-of-the-art molecular laboratory. But even once you get beyond the technical challenges, we have reimbursement. Reimbursement is a major challenge. Reimbursement is not going to happen overnight. We need so many clinical studies. We have to do the right types of studies to prove not only this works, but that it works for payers as well. We have to think about the FDA. The FDA, the FDA is just getting their arms around standard molecular tests. I don't say that critically, it's just where they are. They understand that now they have to learn about a whole new technology which is coming. There is no doubt about it. This technology is coming into mainstream medicine at some point. It'll happen gradually, but it's going to happen over the course of the next several years to 10 years. So we have regulatory and reimbursement challenges as well, and we'll have to work through.
Colin, let's bring you back in the conversation. We've mostly been talking about genomics, and I'm sure Michael's group will be looking at RNA as well. But
yep.
What about the other omics? I mean, what are the limitations of interpreting the genome, and where else do you think we need to? What other things we need to study? Because you've got big, ambitious goals to really help your customers drive, tailoring drugs for a whole slew of diseases, not just cancer.
So I think over the past decade, there's been sort of a lot of focus from certain groups on certain slices of the cell, of the tissue. So some groups very focused on DNA sequencing, some very much on gene expression profiling, some on metabolomics, some on proteomics. And there's been this effort to do, say, standard bioinformatics to try to match variation on one slice through biological material to match that up to clinical outcomes, right? So we had the big rise of genome-wide association studies for a long time, companies like Decode. We had efforts to use gene expression patterns to make a better prognosis in various cancers. Ultimately, if the goal is predicting what the optimal interventions are, patient by patient, and that's the point, I think this is why we're all here at the end of the day, then we do need to have data from multiple layers of the cells, the tissues, and ultimately the outcomes. And so, a lot of our focus, but other people's focuses have also been on being able to integrate DNA sequencing with molecular profiling, with outcomes, and to do this in a longitudinal fashion, and to leverage really fast, high-speed supercomputers. After decades of Moore's Law, we have supercomputers that are really, really cheap. When we started the company 11 years ago, we had a 50 processor machine that was really slow, really expensive. Now that's changed by 3 orders of magnitude. Combine that with multi-layer data sets from a sufficient number of patients, and you have the opportunity to do something that's game-changing. So in other fields, other industries outside of healthcare, people are used to having lots of access to data. In financial trading, they have standardized data that comes in through Bloomberg machines for $1,500 a month. In the world of online advertising, Amazon and Google pioneered big data and big data analytics based on being able to integrate multiple kinds of data and use machine learning to ultimately discover patterns in the data. The biggest limitation to making this practical, to making personalized medicine real, it's certainly the technology pioneers had to do their thing. George and others had to be able to advance the ability to measure things on this granular level. But so far tonight, we haven't talked about how do you integrate the data and use computational methods, not just any computational methods, but computational methods to unravel the underlying circuitry of systems. Whether we're talking about healthcare systems and you're a health insurance company or you're a hospital that wants to better understand care paths. How do you reduce the cost of care for a multiple sclerosis patient using all this data? This is data that's there right now. $2.7 trillion of interventions in this country, producing lots of data exhaust. And so we are, I think, entering a new era where we have the ability to really learn from this data what works in healthcare for whom. And I'm not just talking about the genomic level. I love genomes. Our company's been at it for a long time, but health records in a longitudinal fashion provide lots and lots of important and useful data. And so I think one of the biggest things you're going to see happening over the next few years is the integration of multiple modalities of data, so that including cheap DNA sequencing, but also phenotypic data, outcomes, and other types of approaches.
Yeah, well, I'm coming to you, Jamie. Don't look at me like that. You're next. I want you to follow up on that because you've had fantastic success in finding patterns in data, but it's been mostly phenomic data, to my understanding. It doesn't include, at least for now, genomic data. Do you see an intersection between these two, or somehow all we've been talking about, personal genome data, somehow not relevant to the kinds of patterns and plans that you have with patients like me?
Well, I mean, the nice thing is that genomics needs to look at human beings, and human beings seem to be quite expensive to collect data on, and genomics is getting cheaper, so the longer we wait, the less expensive it is for us to apply. Colin and I are collaborating on a project to try and integrate some of these things. And I actually think Michael hit on a really important point here, and it has to do with this shift in how we think about this problem. So right now, let's go a year ago before Foundation was even operating. In someone we loved had a cancer, and we could do a full tumor profile, and we could do a full genomic sequence, RNA genomic sequence, maybe look at some immune system markers. And we gathered with intelligent people together, and friends and I did this, and then we would make some decisions based on that and the literature and the review about what to do. And it would be incomplete and not exhaustive. It would be a hell of a lot better than the old way of, hey, it looks like you have breast cancer, and here's the two markers you're looking at. So now Foundation's here, and what they've done, and the regulatory challenge they have, is what does it mean to be truthful in saying you've read the genome? And then what does it mean for us to say that's what this means based on this literature? And so they have to establish new standards. What does truthful reading of a cancer genome mean at scale? Because they're not approving a single test like Myriad is. They're approving a whole process. They're going to add genes to continuously, and they're going to reapprove each gene. And then secondly, what does it mean to say that it's, this is related to this paper? So what they're doing is they're saying, Jamie, personalized, your cancer relates to the literature, the history, but not anything I'm learning about anyone else alive today. It's all back reference. And that's awesome because there's, as you said, 18 drugs that match 31 genes. That is, 15 more shots on goal I would have had without the sequence. But that's not the fact that, 50,000 oncologists did experiments on 20 million people last year. And they all did different things in different genomes, and we can learn from any of it that we can use. And so then you go to this next level where Colin has this amazing technology to analyze this kind of data and interact with it, right? And I think that Colin, like our customer, are researchers. We sell this advanced analytics, in my case, of what disease is. What is it like to have a disease? What's the phenomics of the disease? What is the difference in disease at an attribute level from a patient? And it turns out you can actually do a lot before you get anything technical with that. I think we've learned a lot about different diseases in this context and even predict outcomes. But the ultimate extension we really are looking for is a model where, hey, we've certified that we know something about what happened to someone. That's what patients like me really is. What happened? Medical systems don't do that. We've certified some method of reading a critical component of that. Right now it's the DNA of cancer and certain target genes, and then it'll be the RNA of cancer, which is an even harder problem than doing the DNA, right? To get the characterization, the tissue sampling, and things. And then there'll be a proteomics technology that works. And then there will be analytic approaches that run against a characterized human data set, against a characterized set of technologies that we trust. And what are we regulating? And what's the doctor doing? Because what the doctor really does now is distill all of this disparate, disconnected information to make a good decision. Well, humans, they're limited about 10 data points, and you're operating on 400. Colin's networks start at millions. And anytime you really connect any kind of data, you're beyond any human comprehension. So who's the doctor? Where's the liability lie? How does that decision? And when can we imagine a day when it's not just someone like us that are doing the research system, but where anyone can begin to in real time analyze against an ongoing population, against emerging technology, with analytic techniques that are coming to bear. Because if we don't get there, the advances we saw in consumer electronics can't happen in personalized medicine. We can't do this in a regulated, post hoc, certified, Nature Medicine said this was true model of care. And when I talk to the FDA and the EMA about this, they're still asking the question about whether it's safe for consumers to even know their DNA. Let alone what any of this other stuff's happening. So I think this is the shift. and you're seeing the real evolution now, right?
I just wanted to quickly add, I mean, I don't think we are going to get to the results in terms of curing disease without creating a kind of access to data that Jamie just articulated. What we ultimately need from our healthcare system is for it to be an always-on clinical trial.
Yes.
We want to learn every single patient, every single day. We have all of these interventions, not just drugs, stents, doctor visits, operations, exercise, and we don't know what works for whom. We have all this data being collected. It's contained in the databases of many health insurance companies and hospitals, and it will soon include genomic data also, and we do not have a system set up in this country to learn from it. And because of hypersensitivity around privacy, this data is locked away against the best interest, ultimately, of patients. And so that's
the nuance of that, and I agree with everything you said, but the nuance of that, and I think this is the hard part, is that the work that Foundation is doing to figure out how to take a 1 millimeter zero margin tumor, extract DNA, and make meaning out of it that can be useful for a cancer patient, which someone I love will need sometime in the future, is the same work that patients like me is doing to learn that a medical record contains basically nothing useful about the well-being and productivity of the individual experiencing treatment. And you need to actually formalize that process to develop and do that. So I'm not saying that there's not 10 million medical records of hypertension and some prescription data that may be accurate is there. But I think what we're looking at is a problem where there are 10 major advances in the process, characterizing the human condition, understanding whether models create biases or not, and I'm reading into that, or how you run a sample of DNA, how you run a sample of RNA, and how we regulate that. Because what we're doing now will not work. And I think that's the, and what I find really cool is I sit around and I look at, I was a total computer geek, I owned every computer that ever existed. And I watched the beginning of the computer era, you built these damn things, and I look at this, and I'm looking at all the companies, and it's like, who is the first network? Who is the first? Are you VisiCalc? Are you, which is the first commercial software that actually works? Or are you a word processor? Or are you an accounting software? Where are we in this system? What's the market going to be? How's it going to emerge? I think any of us pretend that we know are crazy. Tell investors.
You come up with all these cool things and you call us accounting software?
I want to start taking questions from the audience. In fact, a good show. That's good sign. We're just one quick round because it was by request.